So let's also just change my mouse because I don't like it like that. I'll move this up here. So you said anything in bold you don't need to know. Is that right? So we don't need to bother about describing an experiment to measure the speed of sound in air. Explain what sound is and what ultrasound is. We don't need to bother about that. Relate pitch and volume to a sound wave. Oh, okay, that's a shame you don't need to know that. That's quite interesting. Describe how to use an oscilloscope to measure the frequency of a sound wave. Okay, we won't bother about that either. Okay, so what we do have is describe the difference between longitudinal and transverse waves. We have briefly touched upon that, I think, but we can recap. Define it. So look at what frequency, wavelength, frequency, amplitude is. Describe waves of transferring information without transferring matter. Know and use the wave speed formula. Use the formula relating frequency to time period. Doppler effect. Reflection. Okay, we've got a few things to get through here. Describe what is electromagnetic spectrum, right? Okay, all right. So I'll just get a link to my database and just put that on the same slide. Okay, so there's a link to my database there. This is just an image file, image really, but it's an image of my database. If you click on the N, it'll take you there. So I'll open it up. I'll have a look. I'll show you on my screen now what we've got. So what we'll do is we'll look at the simulations first. That's a good place to start if we're trying to understand some concepts. So let's start off by recapping measuring the different waves. I'll open that up. That's opened up pretty quick, so let's just have a play with that. So yeah, okay. Oh, it's turned on that thing again. Let's turn that off. Right, so set this to no end. Turn damping down. We don't look at damping at GCSE, but you do look at it at A level. And we'll put it on slow motion. So this is so what can we cover in this little animation? We can cover the difference between what a transverse wave is, basically. So you can see that something is seemingly moving from left to right, isn't it? And you'd be right that something really is moving from left to right. But what is actually moving from left to right is a bit difficult to explain. We could say information is moving from left to right. We could say energy is moving from left to right. Or we could say a pattern is moving from left to right. We wouldn't really talk about that in an answer. If we look at any actual part of the wave itself, any part of the string, I should say, let's take these green little circles that have been coloured in, then you can see that that's actually moving up and down. I can prove that. You may be able to see it with your eye, but if I were to get my cursor right there and draw a vertical line, then you can see it stays right on that vertical line the whole time, or just the same distance from that vertical line the whole time. So the individual part of the wave is moving up and down, whereas the wave itself is moving from left to right. The energy is moving from left to right. So we call this type of wave a transverse. And the reason why we call it a transverse wave is because the oscillation, or the vibration, or the thing that's driving it, this thing here, or any part of the string, that is moving perpendicular or at right angle to the energy, the direction of the energy transfer. So we could also refer to this direction as the propagation of the wave. I may have embarrassingly spelt that wrong, but I think that's right. Propagation, I think. So transverse, the way to remember this is if I rotated these two directions 90 degrees, you could write the oscillation, you could draw the oscillation like that, and the energy transfer like that, and then that looks like a capital T, so T for transverse, and there's the right angle to show it's perpendicular. So that's the that's a transverse wave. The other type of wave, which we can't see in this simulation, although I can show you in another one, is a longitudinal wave. And a longitudinal wave still may move, say, let's say down again, like we have done over here, or it doesn't matter. It doesn't matter what direction it's moving. The point is the oscillation into now moving. We say parallel to the direction of the information transfer or the energy transfer or the wave propagation. It's moving parallel to that because it's going the same direction, but sometimes the exact opposite direction. An example of a longitudinal wave would be sound. That's the classic example of a longitudinal wave. There are others, but that's the main one. I think there are types of earthquake waves that are longitudinal. An example of a transverse wave is light, although that's difficult to really get your head around because light doesn't seem like a transverse wave. So a better one to visualize it would be a water wave, which is actually not entirely a transverse wave either, but at GCSE kind of think about it as a transverse wave. And you could also think of a transverse wave as this one here, wave on a string, right? Wave on a string. Yeah. You could get a slinky, actually. A slinky would demonstrate both waves. So you could get a slinky is like one of those called springs, those uncoiled springs that you can use to walk up and down. Well, not up, walk downstairs. And you can get it to make a transverse wave, and you can also get it to make a longitudinal wave. If you had this lesson outside of COVID, you almost certainly would have seen this demonstration done in the classroom. Some of you would have seen it done out of the classroom anyway. So he said, yes, exactly. Yeah, exactly. So the way you demonstrate it with a slinky is you would actually, I guess I could draw that actually. You would actually push and pull the spring. So you'd push and pull it that way. And this would send a kind of a wave of compression from left to right. And you can see those, those are perpendicular to each other. So that's a longitudinal wave, but you could also, if you wanted to, move it perpendicular and it would still send a wave from left to right, and that would be a transverse wave that time. So a slinky can be used to demonstrate a transverse wave or a longitudinal wave. So that's the two types of waves that that you had to talk about. Let me just pause the video and get your list up on my other screen. So that was the first one was talking about the differences between those two waves. Then it talks about determining how to measure the frequency, the wavelength, the amplitude, and the period. Well, the frequency is how many times a wave would go by a particular point every second. So we can take this point here, or if you want, you could take the window. How many waves go by through that window every second? That is what the frequency is. Or it could be how many times any part of it goes up and down in 1 second. That would be the same measurement. That would still be frequency. Or it could be how many times this oscillator, the thing that's driving the wave, how many times that moves up and down. They would all give you the same number. That would be frequency. And that's measured in hertz. Down here, it's actually set to be 1.5 hertz. So that means that in every second, 1.5 waves would travel past this window every second, or 1.5. This would go up and down 1.5 times every second, and so on. I can change that, and if we do, say that again. It may look like it's stopping, but actually all it's doing is slowing down. In order for something to change direction, it needs to first slow down, and then once it's eventually come to a stop, it can go back the other direction, which is why we get this curved. If I pause it, waves have got like this curve, and that's because as it's moving through the middle point, it's actually traveling at its fastest. As it's about to change direction, it slows down, and that's why we get this curve at the top here. So when we speed up the frequency, we start to notice that the waves bunch up together. And the reason for that is because the wave is still moving at the same speed. So the hump of each wave, for example, is still moving from left to right at the same speed, but in that same period of time, that it might take for a wave to go from left to right, this is able to go up and down more times because the frequency is higher. So that means they'll get bunched up a bit more. So I can if I'm going 3 hertz, this is now twice the frequency as before. So that the the thing is oscillating up and down twice as many times every second, and so we're getting twice as many waves in this space. This is linking to the wave speed equation, but I'm kind of jumping ahead of myself here, but I'll just, because this is kind of a revision lesson, we'll just jump around. So the velocity of a wave is equal to the frequency times its wavelength. So we talked about what the frequency is. Let's identify the wavelength. The wavelength is the distance between any two identical points. So we could measure. Usually it's measured from the crest to the crest. If you do that, make sure you measure right from the very top. I've done it wrong as well. Actually, no, I've not done it wrong, but I've not done it in the best way. So I'm going to just change that so it's a little bit clearer. If we are going to measure from the crest to the crest, make sure it's at the very, 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 very top of the crest. So here and here would be fine. Whereas if I did it something like here to here, somebody who wasn't really focusing and doing it in a bit of a rush might do that, and they might lose a mark because it's not you're missing part of the wavelength out, and obviously you're going to get a different value for the wavelength, so it's going to be incorrect. So the top one is correct. So I'll rub out the bottom one. That is the wavelength, and you draw that with this symbol lambda there. Okay, that's the wavelength. So that's Greek letter lambda. So I can just do that. So we know. So frequency is how many times the waves go by every second. The wavelength is the distance between any two identical points of the wave. So I could do it from there to there. I could do it from here to here. I could do it from a crest to a crest. I can do it to any two identical points. The distance it takes before the wave is about to start repeating itself. And obviously there's always going to be the same distance. So that would be the wavelength. So we can work out the distance, the speed the wave is moving by multiplying the frequency by the wavelength, and that is the wave equation. That's called the wave equation, or sometimes the wave speed equation. If it's called the wave speed equation, it's a bit easier to know what it's about. But if it's just called the wave equation, then it means that. It means the same thing. Then there's the amplitude. So the amplitude is how high the wave is. Now, if you had a water wave that's going like this is how they might try and catch you out and say measure the amplitude. You may want to do something like this, from there to there. That would be wrong, because where the water would normally be is at the middle point. See, if I stopped making waves in this water, the water would settle at that middle point, not at the bottom. And in the same way here, it's made it a bit easier for us because it's drawn the dotted line. Oh, can you not hear me? Hang on a second. Okay, so hopefully that should come across it should still be fine in the video. But so basically you measure from the middle point for amplitude. So here they've been nice enough to draw a reference point, but if you don't draw a reference point, or if your exam question doesn't have it, you need to know to draw it yourself or to do it from the middle point. You could also just measure from the top to the bottom and then divide it by 2. That would also give you the amplitude. So that's the amplitude. Okay, so we've done wavelength, frequency, and amplitude. What about time period? What is time period? Time period is the period of time of an entire oscillation, or the period of time of that it takes for one whole wave to pass by a point. And the relationship between time period and frequency is this. So time period is a capital T, and it's equal to 1 divided by frequency, or we can say the inverse of frequency. And in exactly the same way, frequency is the inverse of the time period. So that's the relationship there. So we've covered a few things here. I'm just looking at we've covered the first 5 points there. That's basically all about measuring waves. And maybe another thing to go from here would be to look at the Doppler effect. So I'm just going to pause the recording here. Right, so what should we look at next? I think a good thing to look at next would probably be the electromagnetic spectrum, and then go into the Doppler effect, actually. So let's see what we've got down here. I know I discovered some quite useful things here a while ago. Just gonna see if I can find it. I'll just pause the video for a moment. I need to, if I can find the thing, I need to get this back up again. Okay, I'll just pause this. So we're just having a quick look at longitudinal transverse wave. How do we measure the wavelength for longitudinal wave? Again, it's between two identical points. So in this case, we can say it's the distance between the most compressed point and the next most compressed point. And it's done an equivalent transverse wave underneath. So we can say when it's most compressed, it's at the highest amplitude, and when it's most stretched out, it's at the lowest amplitude. And the equilibrium is where it would be if there was no wave. So let's see if I can find the thing on electromagnetic waves then. Right, so just waiting for this to load up, and this is showing you what the electromagnetic spectrum is. So we know that a light wave is, we know that we can see light waves, and we know it's a wave. It's what we call an electromagnetic wave. And we don't need to know much about that. At A level, you look into a little bit more about what an electromagnetic wave is and what's it got to do with electricity and magnetism. It does have a lot to do with it, but as far as we're concerned, at GCSE, it's a wave, and it's called an electromagnetic wave. Light is just one of the few electromagnetic waves, and if we go down to light, you can see that it actually makes up a tiny part of the entire, what we call the electromagnetic spectrum. And when the wavelength is between these two numbers, the unit being nanometer, which is a very tiny unit, 10 to the minus 9 meters, between these two numbers, we can see it. Outside these two numbers, we can't see it. And in fact, if you just, and you can see what a tiny amount it makes up. So if I move this a tiny bit, you can see that bit's yellow. So now we can see that within that range, we can actually tell the difference between, like, let's say, 541 or 464 and so on. We can tell the difference between these. And the way that we tell the difference is that they're different colors. We see different colors with our eyes. But once it goes outside of that range, we can no longer see it, and it gets a new title. It's called something like infrared. And if you go a bit further, it might be called, also infrared, it might be called, where is it? Eventually, it's going to be called, okay, well, at GCSE, I mean, this is a bit more specific. At GCSE, essentially it's visible light, and then infrared, and then you'll probably get told microwaves. These are just, so microwaves and then radio waves. But this one's giving you a bit more detail here. And you can see these are just really long wavelengths. So radio waves, really, really long wavelengths. And then if you start to squash them up a little bit more, eventually they become what we call infrared waves. And then you squash it down a little bit more. Eventually we can actually see it with our own eyes. And then that's, we call that visible light, of course. And if you squash it down even further, it's suddenly outside of our range again, and now we're into something called ultraviolet. If you squash down even further, eventually you get to something called X-rays, and we know about X-rays. If you squash that down even further, actually, I don't think it's on this animation, frustratingly, but the next one would be gamma rays, which is also a type of electromagnetic wave. So that's so colors are just different wavelengths of visible light, but only within the range of 400 to 750 nanometers. Outside of that range, we have the other types of electromagnetic waves. So now we understand how color works and electromagnetic waves work. We want to have a look at what is the Doppler effect. So let's see if we can find something on the Doppler effect here. Yeah, there is quite a cool thing on radio waves which you can have a look at there and there, but we're not going to go look at that right now because it'll take a little bit longer to explain. So let's see if we can find the Doppler effect. Here we go. Okay, I'll just load that up. So Doppler effect is essentially an effect that happens to all waves, and what happens is if somebody observing the wave, listening to it or seeing it or whatever, or detecting it in some way, they will measure a shorter wavelength if the emitter of the wave is coming towards you. So this animation produces a sound. I don't know if you'll be able to hear it on this because it's coming into my headphones. Well, you won't be able to hear it unless I've shared sound somehow. But the animation should demonstrate it. So we can do it at a slower speed, which is 0.1 Mach. So the animation is nice because she doesn't hear it until the wave hits her. It comes towards her. You can see on the right-hand side, the waves are slightly more bunched up compared to the left-hand side. So she hears a higher pitched sound wave. Now I know the pitch isn't in your list of things to revise, but listen, at this point, and if you were listening to this, you would suddenly hear, I can now hear a lower pitch sound wave. Now, if you do the higher speed, the difference is that the effect is greater. So she'll hear an even higher pitch, and the one behind she'll hear an even lower pitch than before. So the main thing, and let's see if we can find how this behaves if it was light. With our sound, a shorter wavelength produces a higher pitch, so we hear a higher pitch. A longer wavelength produces a lower pitch, so we hear a lower pitch. With light, we know it changes color. So if this galaxy is moving away from us, then the waves that are arriving towards us will be stretched out. So we can do that. You can see that's the size of the speed, and you can see the waves to the right are blue shifted. The waves to the left are what we call red shifted. They're stretched out, and the ones to the right are squashed up. You can change the size of the speed by changing the size of that arrow. When it stops moving, okay, if I move it that way, the effect is reversed. Okay, and I should be able to stop it moving. There you go. And then there's no effect, so either side produces the same wavelength. So this stretching and squashing of the waves, based on whether or not the thing is moving, is called a Doppler effect. And when we apply the Doppler effect to light, we call it redshift or blue shift. Redshift means it's stretched out because it's shifted towards the red end of the color spectrum, and blue shift means it's squashed because it's shifted towards the blue end of the color spectrum. But it doesn't mean that it's red or blue. It just means it's moved that direction. It could be not even visible light at all. So there are still lights being emitted from the Big Bang, and that's being seen or detected as microwaves. And those microwaves, and that's because it's been so stretched, the light's been so stretched that it's no longer visible anymore. It's now beyond infrared even, it's now microwaves. So that's the Doppler effect. Let me just pause that.